Hey everyone, we're going to look at number 7 in section 4.8. This is on Newton's method. I think this may be the last problem in that section. There's only 7 to do. Make sure that you're able to understand this process. We're to approximate the positive root of this equation using Newton's method, and then round that to 3 decimal places. Okay, so I just rewrote the equation here. To me, it seems like there's some simplification we can do. You don't have to do this, but I think this is helpful because later on in Newton's method, we need a derivative, and anything we can do to simplify taking the derivative is good. I just recall that if I have the natural log of something, x plus 4 to some power, remember the natural log of u to the n is just n times the natural log of u. We've used this property multiple times, right, in different settings. So I can bring this 5 down in front, 5 times the natural log of x plus 4. And now I just notice, hey, both sides of the equation, if I divide both sides by 5, which I can do valid, I just get that, right? And now what I want to do is, with the natural log of x plus 4 equal to x, I just subtract x from both sides and I get this set equals 0. That's the goal when you're going to use Newton's method, because what we want to now do is label this as our function. And so we're finding the root, right, which will be the positive solution to this equation. So I want to find the root to this function. Where does this function, touch the x-axis or cross over the x-axis? Okay. Now, you can graph this function, and I actually have done that here. I've put this function in the calculator, and now it helps first to go to a table. I actually went to a table of values and just plotted different values, from -3 here to 4, and sort of got a feel for the outputs here. And that helped me with the window sizing. I'm opening my window from -3 to 5, and then y is going from -3 to 5 as well. And so when I graph it, I can see clearly that the function is crossing through. Let me make this a little darker because it's kind of glaring on the screen. Yeah, I'm making it cross through, right? This is 1 and 2, somewhere between 1 and 2. Okay. In fact, when I plug 1 into this new function, I'm calling this f of x. If I plug 1 into it, 1 plus 4 is 5. I got the natural log of 5 minus 1. If I use my calculator, it's about 0.609. That's a positive number. If I plug in 2, it's natural log of 6 minus 2, which is about what? Negative 0.208, which is less than 0. And remember from the intermediate value theorem that we did earlier in the semester, right? This function f is continuous, since we have, right, the one endpoint at 1 being positive and 2 being negative. We know there's some value between 1 and 2 where the function is equal to 0, where it crosses the x-axis, as we saw graphically as well. So we know we have a root between 1 and 2. I'm going to choose my initial guess. X of 0 is 1.5. And remember, we're going to use Newton's method, and so Newton's method is this method. The next iteration is the previous iteration minus f of that previous iteration divided by the derivative evaluated at that previous. So that's Newton's method, right? And again, you need to watch the lecture video to see where that came from. If you're unsure, I show you exactly where this comes from. Okay. So I do need the derivative, and I found that here. The derivative of natural log of x is 1 over x plus 4, 1 divided by x plus 4. Got a little chain rule, but the derivative of x plus 4 is 1, so that doesn't change anything. And then the derivative of x is 1. So now to find x of 1, right, n is 0, so I have x of 0 minus f of x of 0, f prime of x of 0. I'm using x of 0 as 1.5, and I can plug it all in. I made a little mistake there. I'm really not going to worry too much about this because I'm going to do it all in the calculator, just as I show in the lecture video. So what I'm going to do is, starting with my x of 0, I'm just going to type 1.5 and hit enter, and that stores that into the answer, the ANS, right? And then what am I going to do? I'm going to do answer, right, minus the answer evaluate the function. Remember, here's our function. So this is going to be in parentheses, the natural log of, whoops, already got a parenthesis, natural log of x, which is what, answer, plus 4 minus x, which is answer. So that's my numerator, right, in parentheses, divided by the derivative evaluated at x sub 0, which again is answer. And so that's 1 divided by, and I have to put in parentheses, x plus 4, or answer plus 4, right? Answer plus 4. Close parentheses on that, and then minus the 1, and then close parentheses on the denominator. So that's the derivative in the denominator. And up top, again, if we scroll back, is the numerator, which is the function itself. So this should give me the next value of x sub 1, my next approximation. Okay. And I wrote that down over here. All right, there it is. And so we were supposed to be accurate to 3 decimal places. I would keep going until there's no change in, just definitely sure that there's no change. Obviously, we have a change from this 5 going to a 7. So we need to do it one more time. So we do x sub 2. I'm just going to do second entry, right? And now my input is going to be x sub 1. And so this formula is basically the same, except I have x sub 1 wherever I see an x sub 0, and that's going to give me x sub 2. And it's 1.749. So again, we have some changes in the second, the 5 goes to a 4. So we should do it one more time just to make sure there's no change. And now we're pretty confident, right, by now that it is not going to change. We look like we're all the way accurate, at least out to, the 5th or 6th decimal place. You can do it one more time if you want to, but you'll notice now we don't have any change at all. So this is actually accurate to, it looks like 9 decimal places. Okay, but we only want to round it to 3 decimal places, so that's going to be 1.749. Okay, there's the approximation for this particular example. Okay, and so that's the way you use Newton's method again. Make sure that you can do that. You're going to need the calculator to do that, obviously, to do those calculations, and hopefully this helps with this one.